I know.
A lot of wood burned.
Yeah. No, it's
Not much.
It's a good point. Okay, so what we've been looking at so far is taking water, doing a phase change on it, turning it into steam. That steam causes some vessel to expand and thus making something else move. So from here, a stationary steam engine, if you will, with James Watt, we move on to this character. So this is Trevithick's steam carriage, and I love reading the little, this last little paragraph. It says, Richard Trevithick, a Cornishman and a brilliant and adventurous engineer, see section 6.4, was looking at many options and attracting threats of lawsuit for Bolton and Watt. So there's multiple people working in this same field. Nevertheless, he continued his developments, and on Christmas Eve, 1801, a startling result emerged into the twilight. The age of steam locomotion had begun. It's sort of like chitty chitty bang bang, right? Kind of rolls out. The guys, they'll smoke and billowing, but here he is. This is, predates gasoline, and I'm not sure, it must say here in the book somewhere, but I think he's probably using coal. I mean, that's more or less the most energy dense, but you can imagine using wood or anything that you can convert to steam, get something spinning and hook it up to your transmission, and away you go. And yeah, fantastically inefficient, but hey, beats the other guy who doesn't have, he's still using a horse or whatever. Okay. Now, this next gentleman is really one of my favorite historical figures, and if you're taking 102 now, you'll see why. I've been studying his work for several years now. This is Sadi Carnot. He's a Frenchman, and was really puzzled, bewildered, and anxious about why aren't these things more efficient? What is at the heart of efficiency, and how does one make a machine, a heat engine, more efficient? So let's dig into the equations and look at the Carnot equations. I'm just going to start on page 185 and walk you down through this. It may or may not sink in the first time, but I have a lot of fun thinking about it. And I'll have an accompanying graph here. I'm going to skip that figure and go right here. So in each one of the engines we've looked at so far, you've got some boiler, something getting hot. There's your T for temperature. And if we go right back up here, you can see that T is sitting right there in our heat equation, right? Well, what does that T turn into? Well, it turns into heat. Makes something hot. That goes into the heat engine. Where's the heat engine? Well, it's right there. Trevithick is riding around on one. James Watt built a couple there. Every one of these is a heat engine. Something gets hot and something else moves. Okay. So there's the heat engine. This is the stuff you'll want. You want the water to get pumped. You want your tush to get moved up, down the road to get to dinner at your neighbor's house. That's what you want. That's the good stuff, right? That's getting on down the road. This is what you're kind of left over with. As we know, the end result of energy, any thermal technology, something's going to get hot, the air surrounding, et cetera, and it's going to be to your advantage in general if wherever you're pushing that heat to is colder. And what we're going to see shortly, that unless you actually have something that's hot here and something that's cold here, nothing moves. It's the exact same thing. It's the same reason that photosynthesis works, that the sun actually makes the earth warmer. I mean, if the sun weren't there all nice and shiny and hot and firing energy at us, we wouldn't be here. We rely on those thermal gradients. and we just happen to be sitting in a very special place in our juxtaposition to the sun. And it's really the job of the engineer to design these systems so that they operate as efficiently as possible. So as much good stuff comes out while diminishing the bad stuff. Okay, what do I mean by that? Well, let's look at this first equation. And what we're looking at is W equals Q1 minus Q2. What is this equation an example of? Which law is this? This is the first law of thermodynamics. So right on this one page, we're going to see two laws of thermodynamics emerge. This is the first law of thermodynamics. It is that energy cannot be created or destroyed. Now, what is this stuff? Well, it's work. What are the units of work? It's joules. Work is energy. It is a type of energy. It's measured in joules. What's this stuff over here? Well, this is your heat in. We just saw it, heat input. That's the hot stuff going in. That's, right inside your engine of your internal combustion engine in your car. It's the pressure boilers that we've been looking at so far. What's this thing? Well, it's the heat out. It's the tailpipe on your truck. Or if you're into coal rolling. We were talking about coal rolling the other day, and it's like, yeah, that's just, heat out, a little bonus coal roll, if you will. But, so this is just first law of thermodynamics. So you cannot create or destroy energy, and what we're trying to do is make this work out as high as possible. So the next thing that Carnot came up with is this thing called efficiency, and I'm going to write it with the Greek letter eta. That's the letter H. So if you go into Microsoft Word and type the letter H, and then you convert that to symbol font, you will get the eta, E-T-A. Now, efficiency, and someone said a second ago one of these machines was maybe 2% efficient. What's the highest efficiency you think you might be able to attain?
Well, 100%.
Yeah, you might, yeah. How could you be more than 100% efficient? I mean, how can you get more out than you got in? Yeah. And take that with a grain of salt, because sometimes you'll hear that geothermal systems are more than 100% efficient because they might have, say, a 50-watt pump that's pushing 200 watts of thermal energy. So, but again, that gets back to chapter 1, where we decided what a system is. And if you remember, that's the second word in this energy system. So it comes down to like defining where the boundaries of your system is. There really is no such thing as a system that's more than 100% efficient. But if you draw your boundary and don't sort of include the Earth in your geothermal system, you might come up with more than 100%. But the system we're looking at right now, these are the car or the steam engine. The greatest efficiency you might achieve is 1. What are the units of this thing? What's this measured in? What are the units or dimensions of efficiency? Kind of a trick question. Well,
Joules per mass.
well, you told me a second ago that it was a percentage. So the units are just a percentage. There are no units. The efficiency is going to always be between 0 and 100%, if you will, or between 0 and 1. It can't go lower than 0, and you can't go greater than 1. So efficiency itself is dimensionless. It is unitless. It's a ratio. It would be, in fact, joules per joule, as we'll see shortly. Okay, so eta equals the work out divided by the heat in. So, for example, if I were able to turn all of this heat into work and no waste heat came out, I'd have 100% efficiency. Now, as you may have heard, I'm on this Missoula zero waste bucket or whatever, and we have these fantastic philosophical discussions about whether waste is inevitable or not. So it's like, no, you don't have to have any waste. Well, sorry, every single system on planet Earth has some waste system. I mean, does not matter what it is. If you're not wasting something, you're not alive. You're not metabolizing things. So, yes, sorry, waste is inevitable. It's just a matter of what you do with it, or who's downstream of that waste, if you will. Okay, now, so if we could get, suck all of the heat out of that thing, we would have W equals Q1, and eta would just equal 1, right? We'd have 100% efficiency. But we know from our first equation that W actually equals Q1 minus Q2. The denominator stays the same, that's just Q1. All right, now, hopefully you can see that the numerator is always measured in joules, and the denominator is always measured in joules, and joules divided by joules is just 1. Efficiency has no dimensions. You can measure it as a pure number or as a percentage. Now, if we go right back up here, we can see that Q, or heat, is measured like so. You're going to have some change in temperature. You're going to have some mass. It could be water, it could be gasoline and oxygen. It could be how much steam is coming out of a nuclear power plant, etc. But something's got to get hot in order for a thermal engine to work, and that's what we're discussing here. Now, if we just go and do something like this, equals mass. Well, let's start this way. C sub P times mass times T1 minus C sub P times mass times T2 divided by, and this is not in the textbook, by the way, they kind of saved you the details, C sub P mass times T1. Now, if you'll notice, I just used, instead of specifying a different heat capacity, in every one of these cases we're talking about water, right? So the heat capacity of the water at the first temperature, and again, just getting back here to the boiler. I mean, the boiler is using water. The condenser is also using water. Water has the same heat capacity. There's some subtleties in there in terms of turning something to steam, which we can get into later, but not at the moment. And if we've got a closed system, and for all intents and purposes, if we sort of go back here and look at some of these guys, these are more or less a closed system. I mean, you might have to add a little bit more water now and then, but the water is just sort of cycling between hot and cold. Same thing in the other turbine systems we're going to discuss shortly. In a closed system, the masses are constant. So what you end up with, this stuff cancels, and you're left with T1 minus T2 over T1. Now again, you can measure these in kelvins or centigrades, but again, it ends up being dimensionless. Efficiency is just some percentage. So, what's this mean? Well, it means if I want something to be more efficient, I better have a nice big number on the top and as small a number as I can possibly get on the bottom. Now, what's atmosphere? The other key thing is we have to measure this in kelvins because this is a fundamental. Some people, this is not a precise definition of the second law of thermodynamics, but we're getting close. We started with the first law right here at the top, and we're slowly inching our way towards the second law. for this equation to work out, we have to work in Kelvin. What's the temperature of our atmosphere in Kelvin? About? Usually you talk about 273 sort of room temperature, etc. Easy number to use is 300 Kelvin. So let's just do a really quick and dirty calculation. So if I've got a process, so I'm just going to say eta, I'm going to call it eta 600. And that means I'm going to be able to get my working fluid up to 600 Kelvin. This is going to equal 600 minus, and T2, well, where's T2 in all this mess? It's right here. And in fact, it's just the environment. It's the atmosphere. It's unless you've got some access to outer space, which we kind of don't unless you somehow get up there, we're all sort of sitting here at this atmospheric temperature T2. 600 minus 300 divided by 600 equals 300 divided by 600 equals 3 divided by 6 equals 1 divided by 2 equals 0.5. 50% efficient. Now, it's like, well, gosh, make your coal-fired power plant more efficient. How do you do that?
Change the atmosphere.
According to the second one.
Yeah. Make the atmosphere colder. Okay. Well, in fact, I got to show you this one quick little thing. I gave this talk, and I hope you get a chance to watch it. I had a lot of fun giving this.
I know, so technically we're getting.
Technically, you're shooting yourself in the foot.
Yeah.
So when I gave this talk in Billings, I started right off with the 3 laws of thermodynamics. I said, can our technologies make things hotter, colder, or nothing? Well, there's only 3 ways. I mean, there's no other way out. I mean, things are going to go up, down, or stay the same. So hotter, colder, no effect. So coal-fired power plant hotter, nuclear power plant hotter, internal combustion engine hotter, slash burning hotter, incinerator hotter, greenhouse gas effect hotter, thermonuclear weapons hotter, Homer Simpson standing in the fridge colder, duh, well. So at the back end of that fridge, of course, is heat pouring out. And so that's kind of my point here. Don't. So anyway, I mean, this is a fundamental, irrefutable law of nature that we stumbled across due to the work of Carnot 150 years ago. And we've sort of been struggling with it ever since. Okay, it's 2 o'clock. We'll take a break, and we'll see if we can't finish up the chapter.
I have a question on that, the Bolton Watt steam engine.
Oh, okay, sure. Question. Hey, we'll see you later, Rain. Have a good one. Yeah.
They have the initial water reservoir is that little, square thing.
The large square container is the initial. Let me just make sure I'm talking about the same thing. So this little one inside the big one, yeah.
That's your water source.
Yeah.
Is that water surrounding the condenser and the pump? Is that also water? Is that to hold the heat?
Yeah,
so the heat doesn't dissipate out.
That's actually to hold the cold. Yeah, this guy right here is actually sort of holding the cold, because you can see it's open to the atmosphere. So the condenser is taking the hot gases out of the piston. So this guy's hot.
Mm-hmm.
This guy is hot, expanding back and forth. When that steam is just discharged, either coming out of here or coming out of here,
mm-hmm.
it goes into the condenser. And I guess what I'm not seeing here.
No, but I'm saying the blue around on the outside of that, is that water too?
Yeah, this is water too.
And that's So that's gonna heat up to the temperature of that and kind of hold the temperature better than just having air?
Yeah, it's a great point. And so what you'll,
Insulating.
yeah, the way to think about that, that's sort of like the sweat of the system. You know, so the reason that your body sweats, to keep cool, is as that water that's at your body temperature evaporates, it's essentially taking that heat with it. And so this reservoir, it's big, it's not insulated, it's in direct thermal contact with the air. So, it's constantly sort of shedding or, giving its heat off to the atmosphere, but, on the same note, just same thing in reverse, the atmosphere is constantly giving its coolness to that puddle. And I think, as you guys were saying before, on a hotter day, this thing's not going to be as efficient. And you can even look at this thermodynamic equation we just said. Well, gosh, if I ran my engine down at the South Pole, I'm going to be more efficient, assuming my gas lines don't freeze up or whatever.
But then you gotta take that energy north.
Yeah. So, does that answer your question though, in terms of what's going on in that system? Okay. Yeah. So, I mean, this is all, to me, this is extraordinarily fascinating to study how humans invented these technologies, and it sort of brought us to where we are today. I mean, it's a fantastic journey. I mean, it's just so exciting, to have been there and like seeing these guys come up with this stuff is just amazing. And I think now, I'm really hoping as we sort of move into the next, generation or revolution of energy technologies, we're going to see some pretty cool stuff as well. And just while we're on that topic, I wanted to share with you one such thing. We're not going to get into it. Man, I just blew through these slides so fast. I even showed everyone this little equation during the conference that we kind of struggled with that first day. I think it's an important thing to think about. I got into some kind of weirder entropy things, garbage, burn, there's my efficiency, change, sustainability. There's me. And I got a nice shout out. And I said, "Yeah, keeping it weird in Missoula." that was kind of the quote of the day. Like, oh, they got bicycle loggers in Missoula. These are some other guys that I'm working down in the Bitterroot on, sustainable agriculture and forestry. This is one of the only carbon negative engines in the world that I'm aware of, and it's right here in Montana. This is our electric car. This is a giant pump storage that's going in. This is a paper of mine, but what I wanted to show you was this technology. These researchers, I think they're at a university, one of the California universities, but they've come up with a way to actually allow photons to come in, hit the front plate of this technology. It looks a lot like a solar cell. So right down here at the bottom, you can sort of see these layers. And when you get into 102, we'll talk into the different layers in a photovoltaic cell. The sun's full spectrum comes in, hits the top, goes through these different crystalline layers, and more or less cold air comes off the back in the same way that Homer Simpson's standing there in front of the fridge. Cold comes off the back. Well, what goes in must come out, and then a different wavelength of radiation comes off the front, and it comes off at such a bandwidth or wavelength, if you will, that it fires right through the greenhouse gases. It doesn't get trapped in that CO2 layer in the same way that our sort of ambient surface temperature radiation does. So stuff like this, to me, is like happening right now in labs, and very exciting in terms of, how do you make it cold?
Air conditioning from the sun.
There you go. Yeah, exactly. It's exactly what it is. It's direct air conditioning from the sun. So you can imagine, houses in California, rather plugging into the grid, getting the coal-fired power plant all fired up to send electrons. You're just doing it right there in the house.
Everybody's gonna get sun or sunlight's back.
Yeah,
When sunlight,
yeah,
put that stuff in
yeah.
it.
So anyway, seeing stuff like this is like, they're gonna be writing about this technology in the textbooks, 100 years from now. It's like, here's how humanity figured out how not to cook themselves out of a job.
So as we contribute to global warming, we also want to cool ourselves off.
Yeah. And then it's weird, I've been having these conversations over on main campus about sort of the current reluctance to pursue larger photovoltaic projects on campus. A lot of some of the comments I hear is, well, do you know how much energy it takes to make those solar panels? I'm like, well, yeah, but what's the alternative? I mean, sometimes you're like, oh, are you guys doing alternative energy? I'm like, alternative to what? Like, anyway, good stuff to kind of think about where we are now and where we're going to be in the future. Okay, so we'll take a break, and then I really do want to finish up this chapter. Again, guys, I hope you're enjoying this lecture. I mean, I really enjoy talking about this stuff. I mean, it's just